You're recording, so be careful.
Good afternoon, everyone. This is Charles Robinson, the Workforce TAC Vice Chair, Quantum Economic Development Consortium, filling in for Adrian German, who's the TAC Chair, and I will be moderating today's e-poster session. We have a tremendous group of young researchers that are going to present their research today. As you guys join in, I'm going to, describe each individual's bio and the work that they're going to present. And at the end of each session, if you have any questions, please put your questions in the chat. We're going with the Chatham House rules, but we want this to be a free-flowing dialogue. Please let these young researchers present fully, and we'll address your questions at the end. And with that, I'd like to introduce our first graduate, Ugne Dargyte, is a fifth-year graduate student from the University of Nevada, Reno, from Dr. Weinstein's group. She's been studying optical properties and spin coherence lifetimes of alkali atoms in matrix isolation systems for quantum sensing applications. Her research area that she's been working on was from the most sensitive magnetic field detectors in the world are atoms as quantum sensors. In her research, she aims to put our sensor atom in an environment in which a single atom is capable of detecting a single molecule. And she does this by implanting sensor atoms alongside of molecules of interest inside solid neon. So she's going to talk about that research. And she also has interest to her dream job to work for Honeywell and IBM, go IBM. And I'm going to turn it over to her right now.
All right, is the audio okay? Okay, so thank you very much for the introduction. And thank you for having me here today. So I'll be talking about some of the work that's being done at Dr. Weinstein's group at the University of Nevada, Reno, in creating a single atom quantum sensor. So I would also like to take this moment to acknowledge David Lancaster, who's the other graduate student working on this. And if you want any more information on kind of the topics that I'm covering right here, we have recently published a paper that's put down on the bottom here. Okay, so our goal is to perform an NMR spectroscopy of a single molecule. So in order to do that, we need an AC magnetometer that's sensitive enough to detect the magnetic field of a single nuclear spin. So because atoms are the most sensitive magnetometers to date, that's what we're going to be using, but the field of a magnetic dipole falls off as 1 over r cubed. So the way that we can achieve the maximum sensitivity is we want to co-implant our molecule of interest. So that would be our diagram right here, alongside our sensor atom, rubidium, inside a matrix, so solid neon. So for this talk, we're just going to be talking about sensing with an ensemble of rubidium atoms. And the requirements for creating a really good AC magnetometer is that we want favorable optical properties. So we want to be able to prepare and read out our spin state, as well as long spin coherence lifetimes. So specifically for AC magnetometry, that's T2. So here we see a diagram of kind of our cryostat, our setup. So we grow our samples through vapor co-deposition on a sapphire window that's sitting at 3 Kelvin. We can access our rubidium atoms through 2 windows that's sitting on either side of the cryostat. And we typically grow our samples of rubidium densities of 10 to the 16 to 10 to the 18 per cubic centimeters. Our thickness is a fraction of a millimeter. We can also vary that. We have 2 permanent magnets on either side of the cryostat, and this allows us to currently work at 2 magnetic fields up to 100 Gauss. So here you see an absorption spectrum of rubidium doped neon, as well as undoped neon sample in the black line right here. So the really important thing to notice here is that these absorption lines are much broader and shifted from the free atom case. And do you see multiple absorption lines, which we believe result due to multiple trapping sites? This is due to the polycrystalline nature of our sample because of vapor co-deposition. So typically we park our laser at this wavelength, like 786 nanometers. And we are, for the remainder of the talk, we're just going to be talking about atoms that are accessed through this trapping site right here, where our laser sits. So going back to the requirements of a good AC magnetometer, we want to be able to control and read out our spin states. So here we see a diagram of our optical setup. This here is our sample on the sapphire window. We can optically pump our atoms using right-hand circular beam at 786 nanometers, as again indicated right here. And then we can probe our state using circular dichroism. The way we do this is we have weak probe beams, which is a combination of left-hand circular and right-hand circular probe beam. And we measure the relative transmission of each one of those beams. So on the bottom right here, you see the transmission as we optically pump. So the transmission of both the right-hand circular and left-hand circular beams are normalized before optical pumping, and then at t equals 0, we start to optically pump. We see that there is a roughly 10% difference between the transmission of the right-hand and circular beam. And then as our spins relax back to their equilibrium states, that ratio then goes back to 1. So here we see that the ensemble spin state dependent contrast is roughly 10%. Kind of for comparison, we would expect roughly 100% for gas phase atoms. However, because we have our atoms implanted in the matrix, we have a lower readout. However, this is good enough for what our purposes are. So here we see that we're able to control and read out our spin state. Now, what about the coherence lifetimes? So here is the rubidium, the ground state energy level of rubidium-85 isotope. That's what we're sampling as a function, the energy splitting as a function of the magnetic field. So the nonlinear Zeeman shift at the magnetic fields that we work at allows us to resolve the individual m's of f single photon transitions. So we can measure the lifetimes of a chosen transition. So our T1 lifetime is on the order of 1 second. Our ensemble dephasing time is on the order of 10⁻⁵ seconds. We have previously studied the nature of this shorter lifetime, and it's due to inhomogeneous broadening of our ensemble, specifically due to electrostatic-like interaction with our host matrix. We have been able to enhance this ensemble lifetime to the order of 100 milliseconds using dynamical decoupling. And it's important to note here that this T2 lifetime is the longest T2 lifetime recorded in a solid state system at the densities that we work at, 10 to the 16 per cubic centimeters. So we're doing well with the readout and preparation. We're doing well on the coherence lifetime. Now, can we use this ensemble as a AC magnetometer? And we can use this using dynamical decoupling. So we're going to do this by measuring the T2 lifetime of our F equals 3 MF 0-1 superposition state. Our pulse sequence of choice is the alternating phase Carper cell, which you can see shown right here. It's a equally spaced pi pulses at equal time of tau apart from one another. We call it the alternating phase Carper cell sequence because we've rotate the phase of every subsequent pi pulse by 180 degrees to kind of compensate for potentially incorrect pi pulse rotations. Now, the dynamical decoupling sequence for this measurement has 2 effects. One is that it's able to decouple from environmental and magnetic environmental noise inside our matrix, as well as increase the sensitivity to chosen frequency. This is where that AC magnetometer is coming in. So here we have our T2 lifetime of our ensemble of spins as a function of APCP post frequency. So this is just 1 over the time delay between our pi pulses, which we can vary. So in addition to just having that overall trend of increased lifetimes with increased pi pulse frequency, we also see this distinct dip here at roughly 62 kilohertz. Now, because we're putting our rubidium atoms inside neon, we have the magnetic neon-21 isotope. If you look at the precession frequency at the magnetic field of 95 Gauss, where this measurement was taken, it actually matches up really well with where we see our dip. And in order to verify this, we're actually seeing neon-21 nuclear precession. We're going to go up in magnetic field and see how this changes. So while the overall trend of this measurement with increased lifetime is the same, we see that this dip is changing now with increased magnetic field, which is again corresponding really well to our with our neon-21 precession frequency expectation. So this is really good. This means that we can detect the magnetic field from neon-21 with our rubidium ensemble. So we have created an AC magnetometer, which is capable of detecting nuclear spins. Kind of some information on how we're doing with the neon-21 isotope. There's natural abundance of 0.27%. So this would correspond to an average distance from rubidium to neon-21 of about 10 nanometers. Our line width is actually 20 kilohertz, roughly 20 kilohertz, which is wider than the solid neon NMR line width. We believe that this is because we're sensing with an ensemble of rubidium atoms. This is why we have this broadening effect, and that this ensemble has inhomogeneous broadening due to the magnetic field of rubidium. So there's some dependence on the rubidium density as well. So what's next? So in this talk, I've shown you that we're able to use rubidium atoms as AC sensors. We can prepare and read out the spin states of rubidium and solid neon. We can detect a single nuclear spin 10 nanometers away. Our goal now is to scale down from an ensemble of atoms, rubidium atoms, to a single atom magnetometer. So we have successfully shown that we can actually detect redshift fluorescence. That's going to help us with readout of a single atom. And once we're able to perform NMR spectroscopy of the neon-21 using just a single atom, we can then move on to actually implanting molecules of choice inside of our rubidium and then using for MRI spectroscopy. And with that, I'd like to complete my talk and thank you all for your attention. And if there's any additional information, there's a website for this group that has all of our published papers as well. Thank you very much.
Thank you so much. That was very well done. Very succinct, very compact. It was an outstanding presentation. And so I'm going to check here to see if there's any questions in the chat. I have some thoughts here. Don't be shy, folks. But one of the things that I wanted to talk about, and I just want to make sure I understood clearly. Probing with circuit dichromism is something you talked about, and you mentioned the T1 time at 1 second and the T2 time at 10 to the minus 3, and you said it was because of dephasing in a homogeneous broadening process, and that was how you got down to a T2 of 0.1. And so I wanted you to again describe that for me, because to me that was the special sauce. And but you kind of went faster. If you can work through that again, pull that slide up and explain that to me.
Let me just pull up the slide in a second, and I'll be able to go through it.
That amongst many. Mm-hmm.
Yeah, I think I did go through it. 1 second, sorry. Okay, so our T1 lifetime, that's just if we optically pump, how long does it take to get our spins back to equilibrium? So that's kind of our upper limit on all of the other lifetimes. So once we go back to equilibrium, we no longer have polarized spins, so we can no longer kind of read out the superposition of the states that we choose to. Our T2 star, that's just the dephasing time of our ensemble of spins. So if there's some kind of inhomogeneity among our spins, so for example, since we're reading out, let's say like 10 to the 11 atoms at a time. If they're all experiencing a different magnetic field, they're going to be processing at a different rate. And that's what's causing that dephasing time amongst our ensemble.
Gotcha.
But there's kind of tricks that we can play, kind of those NMR sequences, where we can actually compensate for some of that inhomogeneous broadening. And that's the APCP sequence, which again, the dynamical decoupling has the two effects of, we can use an AC magnetometer, but we can also we can use an AC magnetometer, but we can also eliminate any kind of magnetic noise sensitivity of our spins, because we want to just measure one thing and kind of not be sensitive to the other one.
That's right.
And that's where this graph kind of comes in, where we see that as we're going up and up in frequency, we're increasing our lifetime from here like 60 milliseconds to over 100 milliseconds for the specific range of frequencies. And this is because there's some kind of low frequency noise that our rubidium spins are sensitive to. So for this instance, it could also be like the flipping of the neon 21, the T1. And by just kind of correcting our dephasing time faster than the magnetic noise, we can elongate our T2 lifetimes. So that's what makes it a really good kind of sensor.
Yeah, that's what makes it a really good magnetometer. So that is really the crucible of what you talked about. I just want to make sure those were looking at this. So as the magnetometer, can you talk about, you told me about where you guys are going in terms of your next generation research effort. But can you talk about some of the, from a practical standpoint, some of the applications of this magnetometer and what it could be used for? I mean, magnetometers are used everywhere, but for this type of sensitive magnetometer, what do you foresee as its current usage, and what applications are there that this thing will be used for?
That's a good question. So again, having that magnetometer, the long-term application is actually to perform NMR spectroscopy of just a single molecule, as well as MRI spectrums as well. So if we're able to just kind of implant whichever molecule we want inside our solid, and this is kind of the advantage also to what the leading states, so like nitrogen vacancy centers in Diamond, they've already done nano NMR and MRI very successfully.
Yes.
And a lot of our work is actually kind of built upon what they've been doing. And they do it really well. But however, they kind of do have the limitation that they're limited to what they can sense, because it is a diamond. So they're sensing their carbon-13 nuclei. If we're able to successfully detect a single atom, then we can, because we have that vapor co-deposition method of growing our samples, we should be able to just kind of image whatever molecule we want. And that's that applications of being able to really have that option of what we want to image.
Outstanding. Are there any other questions? I think that this is really great work, and we really appreciate you presenting at the QED-C poster session. And for those out there who work for IBM and the other companies she's interested in, I'm not going to mention, well, Honeywell, she's interested to work. And so thank you very much.
Thank you very much for having me.
Awesome. So next up, we have Alex Kato, who is a former engineer turned graduate student studying atomic physics. And that's a man after my own heart, being an engineer myself at the University of Washington in Seattle. As a graduate student researcher, he's studying trapped ions, qubits in the lab, and he focuses on single ytterbium ions, as well as two-dimensional formations of trapped ions. And so he also, he's doing some amazing things. He won the Alfred P. Sloan Award. He speaks French and English, and he's worked at Co-Quantum. As a Bachelor of Science in Physics, he graduated with honors from McGill University. And so even at McGill University, he worked in in the optical mechanics laboratory. And so what he's going to talk to us about today is the attempt that he's doing to create a hybrid quantum computing system composed of trapped ion qubits and solid state qubits. And also, both qubit systems happen to emit light at the same frequency at 369 nanometers. And he hopes to exploit this to establish entanglement between the two systems. And such a hybrid system, he believes, would benefit from the long-term coherence time of trapped ions and the fast gate speed as solid state systems. So with that, Alex, if you could go ahead and give us your presentation, we'd all appreciate it.
Great, thank you, Charles.
Mm-hmm.
All right. So as Charles mentioned, I study trapped ions here at the University of Washington. And you see this question mark here. So this collaboration, we are working with a lab just down the hall, Kai-Mei Fu's lab, where they work with another kind of qubit. The kind of qubit that they work with is what I call a donor qubit, which is composed of like a donor impurity within a bulk crystal. So you may have heard of things like NV centers. It's related to that, but a different kind of crystal. This crystal is zinc oxide, and the donors inside are slightly different. They might be indium or gallium or aluminum. And okay, so this project all kind of started because in Kai-Mei's lab, in this new qubit system, they have this really cool optical transition at 369 nanometers. And if you're an ion trapper, that immediately should ring a bell, because trapped ytterbium ions, which happen to be possibly, arguably the best trapped ion qubit that exists today, also has an optical transition at 369 nanometers. So Boris and Kai-Mei kind of got together and thought about, how can we think about establishing a connection between these two systems? For one, it just happened to be down the hall, and two, it's only about 50 meters. So if we could figure something out, all we have to do is send light down an optical fiber, and we can hopefully get some kind of experiment up and running. So just a little bit of background on the two different qubit systems. I'm not going to go over too much here, but basically in ytterbium, the transition we're talking about is at 369.5 nanometers. And it's a pretty commonly used transition in ytterbium. It's used for Doppler cooling. So in this image here, we have an image of a single ytterbium ion, and this ion is being cooled by the Doppler cooling laser at this frequency. And we are taking an image of the photons scattered by the laser. Over here for the donor qubits and zinc oxide, this is kind of what's called a PLE, or photoluminescence spectrum. What you see here are different energy level peaks that correspond to different impurities. And if you could convert these to wavelength values, you would see they're quite close to ytterbium. There's still quite a large frequency gap. And I'm going to talk a little bit more about how we might bridge that so we can directly come up with a way for these systems to interact. Okay, so let me take a step back for a second and talk about why we would want to even do this in the first place. So I work with trapped ions, and I'm going to lump this together with neutral atoms and call these atomic qubits. And these qubits are really nice because they're very well isolated from any kind of background gases or anything like that. And if you have a single atom, in our case, a single ion, they have very long, what we call coherence times, or which would be related to the properties that you might desire in a quantum memory. Additionally, trapped ions have also very good, what we call gate fidelities. And this is just a measure of how well you can do quantum gate operations. But trapped ions also suffer from one downside, which is that generally the speed of these quantum gate operations is quite a bit slower than that of solid state systems. And when I say solid state systems, I mean superconducting qubits, which I'm sure everybody knows all about, and other solid state qubits, such as the donor qubits and zinc oxide that I'm discussing today. So solid state qubits generally have quite a bit shorter coherence times than trapped ions. However, the fidelities have gotten up close and pretty comparable with that of trapped ions. And also the gate speeds are much, much faster. So the idea here being good coherence times in trapped ions combined with fast gate speeds of solid state qubits would give you some kind of hybrid quantum system that benefits well from the best parts of both different systems. All right, so how could we go about doing this? Well, our first idea here is just to do a simple entanglement experiment. So this is an experiment that was first done with trapped ions. So here, that's why I show you two trapped ions. And what I'm going to describe to you here is just how you would kind of transcribe this experiment from using two trapped ions and replacing one of these with this donor qubit in zinc oxide. So this, if you want to read more about it, is called the weak excitation scheme. And how it works is you basically, so you prepare both trapped ions in the same state, and you weakly excite them both. So what you want to do here is have a small chance of both systems emitting a photon. Except you only want one of them to emit a photon. That's the key here. You interfere the paths of these two photons, A and B, in a beam splitter, and then you have two detectors. And when you detect a single photon on either detector, if you don't know where it came from, we call this also witch path erasure. It projects the state of these two ions into an entangled state. So basically, upon detecting a single photon, we have come up with an entangled state of our two systems. And these two systems could be, they could be two ions in the same trap, but they could also be two ions in two different labs. So imagine I'm talking about Kaimei Fu's lab down the hall. If we were to replace one of these with that solid state qubit I was talking about, the goal here is that we could do this remote entanglement experiment and entangle the two systems.
Okay.
So the question is, can we do that? I mean, it sounds easy. I can just replace one of the qubits with a different type, but it turns out there are quite a few problems associated with that. So the goal here then is if we can make this other qubit look like a trapped ion, then we could perform this experiment. And how do you do that? Well, you have to make the photons look the same that are emitted from both systems. So I talked about the systems both having photons at similar wavelengths. So that's already kind of a plus. That's going to really help us out here. But you also have to match things like the spatial mode and the polarization of the emitted photons, as well as their temporal shape. And what I mean by that is it's basically a probability in time of a photon reaching the detector. So really quickly here, we'll take a quick look at the energy level structure of the qubits. On the right here, we have ytterbium. So this here being our Doppler cooling transition. And if we call one of these, so these states are split up into hyperfine structure by their nuclear spin. And so if we can encode the one state in one of these F=1 ground states and the 0 state in the F=0. And with the donor qubit in zinc oxide, we have a ground state, which is this D0 denotes a donor with a bound electron, and that's the ground state. The 0 and 1 are the Zeeman levels. And these are, so you have one electron, the electron has spin up and down, so you get these 0 and a 1. So we did a magnetic field basically to split these states. And the excited state is a donor, a bound electron, and what we call an exciton, which is a bound electron hole pair. So we use one of these states as the excited state, and then this transition here is at 369 nanometers, same as the transition here. Well, they're not exactly the same, but as I described, they're close. But one of the big problems here is that the line width or the lifetime of these transitions is drastically different. It's about 8 nanoseconds in ytterbium, but only about 1.4 nanoseconds in zinc oxide. And what that means is their temporal profile, as I was describing before, is drastically different. So these qubits are going to look, they're not going to look the same when we try and do this experiment. So we need to do something to try and make them look the same. And so one of the ways we can do that is by incorporating the donor into an optical cavity. And what that allows us to do is basically delay the emission of the photon from the zinc oxide, the donor qubit in zinc oxide. And so we can use a technique called pulse shaping, which is a fairly well-established field at this point. And you can basically change the shape of the pulse that you're using to excite the donor qubit. And what that does is change the shape of the temporal profile. So we basically engineer a pulse to make the temporal profile of the donor qubit look like a trapped ion. And that can be done, for example, with an AOM, which is a common tool in atomic physics, basically just by turning the laser on and off at the desired time. And in some of our recent results, we haven't actually done this yet, I will stress, but we've done some calculations to show that you can achieve a 99% temporal overlap with some pretty simple pulse shaping techniques. Finally, just talk a little bit about the ion trap that we're actually going to use here for the experiment. So in our lab, we have this really neat ion trap. It's composed of a parabolic mirror and a needle. And a parabolic mirror is a very interesting optical device. It's used commonly in many different systems. I like to give the analogy that it's used in a flashlight. And if you put the bulb right at the focus of the parabolic mirror, all the light that comes out is collimated, forms a nice collimated beam. In the lab, that's very useful. Collimated light is nice. It's easy for us to kind of calculate spot sizes, things like that, and design a system where we can actually focus all of that light and couple it into a waveguide or optical fiber, which is something that will be very useful for this entanglement experiment. So this parabolic mirror is actually part of the ion trap in this case and allows us to collect collimated light and focus it into an optical fiber. Here I should mention a lot of this new trap design was done by a fellow colleague and graduate student or former graduate student, Jennifer Lillyhold in our lab. Okay, so I'm running out of time here. I should probably finish up. But basically what we want to do is couple together our trapped ion and the solid state qubit down in Kaimei Fu's lab. And we want to do an entanglement experiment with them, a remote entanglement experiment. And to do that, we need to make the solid state qubit look like a trapped ion. And what we talked about was all the different challenges we'll have to overcome to do that. Great. I just want to give a shout out to the whole zinc oxide team who are doing a lot of the great work that makes this all possible. Thank you.
That was awesome. Thank you so much. That was a really great presentation. Let me check the chat here to see if there's any questions. Give me 1 second here. All right, no questions in the chat. So it struck me when you talked about you believe based on calculation that 99% of the overlap by using that model that will get you to the photon temporal state where it will be the same, and that you use those calculations, you know, so that would lead to a level of optimism when you do this experiment but have you taken in consideration the environmental factors here about, you know, setting up that experiment? And obviously, you know, we want to do this experiment. You're going to do it in the lab. There are some environmentals here. What are you looking at in terms of the expectations of how that will impact this?
So that's a great question. It's a hard question to answer, being not having actually done the experiment, but we do know that if we were to set this up and run it, that indeed I would not expect that we would achieve this 99%. This is a very theoretical value.
Of course.
So there are going to be a number of sources of noise associated with, you know, some of it's just going to be lost in the system. Like there's optical losses. We're not going to collect the amount of light that we have set out to collect. You know, it's a very optimistic value. You're going to have a few % loss here and there. We'll have a long optical fiber that connects the two labs down the hall. There's going to be some loss in there. And additionally, I didn't talk about many parts of the experiment, such as the optical path length of that fiber will need to be stabilized and known, because the outcome of the experiment depends on it. So you need to have some sophisticated feedback in order to do that. And you're going to have a lot of thermal fluctuations within things like the fiber itself, which will introduce noise into the system and reduce what we call the fidelity of the entangled state. So that's some of the sources of noise. Also, there are going to be some other sources of noise in the zinc oxide system. One of the outstanding issues that's going to need to be overcome is isolating a single donor. So if we could have a single donor qubit, that's the ideal thing. Then you have a single trapped ion, a single donor. They're both more well-defined, but with an ensemble of donors, which is what currently we're looking at working with, there's a lot of inhomogeneous broadening, as the previous presenter was talking about, and things like that, that reduce, well, that basically, and I don't want to talk too much about that, that's not my area of expertise, but can make this kind of experiment a lot more complicated. So we would have to come up with a way to adapt this experiment to work with an ensemble instead of a single donor qubit.
Well, let's first get it to work with one, and then we'll work out. We'll get to that later. But Alex, this is very exciting. Please let us know how the experiment works. We're all very interested in this. If you can actually use the best of both modes, trapped ion and the other method. I mean, that this is groundbreaking stuff. So we really want to hear back from you on this. All right.
Great.
All right, well, no worries. Next up, we have, and we're running 5 minutes late, so I need to pick up the pace. We have Botao Du, who received his Bachelor's of Science in Physics from Tsinghua University in 2019, where he started his undergraduate research on trapped ions, quantum simulation with Professor Ki-Wan Kim's group. After that, he started his PhD at Purdue with a focus on quantum simulation and superconducting qubits. And his primary research interests are quantum simulation experiments, AMU, and related experiments, and the work that he's proposing using engineered thermal bath environment to help stabilize novel states in quantum systems. And one aside, he wants to be a quantum experimental scientist at IBM, Microsoft, and Google. So with that, you can have the floor.
Thanks, Charles. Okay. Share my screen. Okay. Can everybody see my screen?
Yep.
Good. Hello, everyone. My name is Okay. My name is Botao. I'm currently a third-year graduate student working at Alice Math Group at Purdue University. Today, I will talk about driven displacive dynamics in superconducting circuit lattices coupled to quantum buses. Superconducting circuits has been well known as a great platform for quantum computation and quantum simulation because of its advantages. For example, the high coherence, precise qubit control, high fidelity measurements, and etc. For our group, we are mainly interested in analog quantum simulation, where we can view superconducting circuit as a synthetic photonic matter, which is made of microwave photons. And people can use it to investigate a lot of interesting physics phenomena based on the system they have engineered. But nothing is perfect. There are still some challenges. For example, there will always be intrinsic loss, which will lead to the lack of photon number conservation. But in some sense, that could also be an opportunity. Dissipation is usually not favorable in a quantum system because it can lead to decoherence and can finally destroy the quantum state in our system. But can we use dissipation as a resources, or specifically use dissipation to prepare or manipulate a quantum state? The answer is yes, and we already know how to do that. One example is the optical pumping scheme, which is widely used in different experimental systems, where people can use a coherent pump to continuously drive the system into the high excited state, which is relatively lossy, and it will quickly decay to a metastable state. And finally, the steady state in such a system is basically the metastable state. And this simple model already shown us the main idea about how to use driven dissipation to prepare a quantum state. With driven displacive buses, people have already achieved entanglement states. People also achieved arbitrary single qubit state validation with the help of driven dissipation. Going further, we can even use it to realize autonomous quantum error correction. And the appearance of tunable dissipation advanced technique we can use to actually engineer our buses. For our group, we are mainly focused on using driven dissipation to study the strong correlated many-body states. You can think a many-body system as a generalized version of the three-level system. With proper bus engineered, the pump will help us bring it into the strong correlated state, and the lossy channel will help us get rid of any unwanted excitation inside the system. There are already some interesting results in the field. For example, people have already realized dissipatively stabilized multi-insulator states, which is also one of my PI's previous work at UChicago. Their main system is made of 1D basalt lattice based on transmon qubits, where you have on-site interaction U and nearest neighbor tunneling J. The idea is that if you couple your lattice with a single with a particle sources, for example, a site that always has one photon, then the photon in your bus will propagate into the lattice. And in the steady state, you have average one photon in each site. For J much smaller than U, this is called the multi-insulator state. In their case, they only need a narrowband bus to realize this multi-insulator states. Because if you look at any spectrum, you really just need to cover the first band to stabilize multi-insulator states, which is good for experiment. But for multi-insulator states, the on-site fluctuation is relatively small, and so the final state is quite close to a product state, and the density correlation is really small. To stabilize a many-body states that has large correlations, we probably need to go to a system with smaller gaps and low energy excitations. One example again is in basalt lattice, but in superfluid regime instead of multi-insulator stream, where J is comparable with U or J is larger than U. And there are already some positive theory predictions about that. The first feeling is probably we can use the similar techniques they develop in the multi-insulator experiment and just use it in superfluid regime. This is a good idea, but not 100% true, because to stabilize a state in superfluid regime is you need a much more complicated buses. If you look at some energy spectrum, you no longer has those like gapped energy bands. They are basically mixed together. And what this theory paper told us is to stabilize into to stabilize this superfluid states, we need two buses. One serve as a gain and the other serve as a loss. I will explain why that is needed in the next two slides. To stabilize the superfluid states, we will engineer the two broadband bus in this way, such that the photon propagate into the lattice always has a lower energy, and the photon travel back to the buses always have a higher energy. So we can say the frequency where the loss is equal to the gain is kind of the chemical potential of our system. And the sharper those edges you can engineer, you are closer to the zero temperature situation. Another way to look at this is switch to the ground canonical ensemble, where we take the chemical potential into account when we're talking about the total energy. Let's say if you get a photon from the bus, your total energy is actually dropped because the energy of the photon is always lower than the chemical potential. And similarly, if a photon travels back to the bus, the total energy will also drops. So in the end, the total energy will be minimized and stabilized to the many-body ground states. And with proper bus engineer, this many-body ground state could be the superfluid state that we're looking for. Based on those analyses, we did a very simple simulation for 4 sites for lattice with some realistic parameters. You can you can see the lattice quickly get to the steady state, and the final correlation we have in the steady state is quite close to the ground state correlation. And the steady state also has a high fidelity with the closed system ground states. Moreover, this theory paper also shown us that high fidelity can also be achieved in a broad parameter space. Of course, we have to think about the effect of bus temperature, but the good thing is the thermal population can also always be well controlled in actual experiments. So what can we do in actual experiment? Let me quickly introduce you about our proposed experimental system. Similarly, we have a 1D Bose lattice to form our many-body system, and this is made by transmon qubit basically. And there are tunable coupling between each side, so that we can go all the way from the multi-incidence regime to the superfluid regime. There are broadband bus coupled to the lattice, and we can dynamically tune them to make them serve as a gain or serve as a loss. And we can also couple them to whichever side we want. As an example here, we place them on the two ends of the lattice so that we can do transport type measurements. For example, we can measure how does the population and correlation forms and transport inside this 1D lattice. Finally, there will be readout resonators, Purcell filters, etc., to help us realize fast, high fidelity readout. The next main step is think about how to engineer the broadband buses. The quick answer is each type of these buses can be built by using transmon qubit. For the gain bus, we can think transmon qubit as a 3-level system. We continuously draw the qubit to the 2-photon state. And the qubit is coupled to a lossy resonator, which is resonance with the 2-to-1 transition. So it will quickly decay and finally stabilize in the single photon state. In this way, we formed a narrowband gain bus. And the line width is determined by kappa, and the height is basically determined by omega. To make it broadband, we can imagine to have a lot of copies of these narrowband buses at different central frequency. In reality, that could be realized by temporarily sweep or detune the qubit frequency, which is quite natural in superconducting circuit system. For the dream bus, it is kind of even easier because we don't need a pump. We only need to couple a transmon qubit with a lossy resonator that is actually resonance with a 0-to-1 transition, and in similar way to make it broadband. And all this process can also be realized by using sideband transitions. All I talked before is what we think to do right now. Going further, there are also a lot of interesting we can investigate more. There are already theoretical proposals about creating and manipulate entanglement many-body states using driven dissipation. We can also study about out of equilibrium quantum dynamics and driven dissipation, dissipative phase transitions. In general, we can also explore more about the role of non-classical noise in a quantum system. Okay, that's basically all of my presentation. Thank you for all of your attention, and I'm glad to take any questions.
That was awesome, and obviously, at IBM we're doing transmon qubits, and so some of the work that you're seeing here, that you're presenting here, I'm not unfamiliar with. And you talked about the 1D Hubbard tunneling work, and then next would be working on multiple systems, and that's what I wanted to talk to you about was the crosstalk noise in the environment here, and the experimentation of what you were doing here, and the impact of that. Have you looked at that, Alex? And Botao, and how did that impact the performance of that experiment? The slide that you showed, it had. Let me go back one more.
Yep.
Keep going. That was how you do the gain and loss and the back between qubits. And this is the 1D Bose-Hubbard tunable tunneling. How is the crosstalk impacting this architecture with your gain bath and your loss bath, and your two tunable baths, the way that you're doing this. And did you characterize that? And was that a part of the research that was in those two papers down there? Because they all impact one another, right?
Yeah, true. That's a good question. So actually here we haven't, so all we're doing now is just kind of theoretical analysis to see how can we actually form those broadband buses. Yeah, it's true that in the end, the crosstalk between the qubit could be a problem if you don't take care of that. But I think maybe one thing we can try to minimize, or to eliminate the crosstalk, is just try to place the qubit at different frequency, and then have kind of a tunable coupler between them. So that's when you are not actually when you are not actually processing any pulses to the system, you just isolated those qubits, so that you basically bring them to a different frequency regime. But yeah, that's true. Like in the end, if you have if the crosstalk is a issue, it will definitely affect the final, what I'm showing. Sorry, what I'm showing in the previous simulation, like it will definitely affect the final, like the ground state fatalities. Yeah, it will affect.
Like 1 to 2, 2 to 3, and 1 and 3 to 4 will be impacted by that. And so the correlation and the ground state that you have 93.3%, that I just want to make sure that, you said that those are next steps. So I just want to make sure that you are looking at that. I know we're looking at a lot of this at IBM, right? Because we're doing
yeah. And I think the kind of the flatty I shown here, because I mean, when we're doing the simulation, we just imagine, okay, there's 0 crosstalk. So this is basically eliminated by the model we use to realize those broadband buses. And I would say, like in actual experiments, it actually probably will be even worse, because this is ideal analyze, and in experiments, your bus couldn't be exactly what you want. Yeah.
More importantly, if you can model it, that's the piece that's valuable. Obviously, there's a lot of work in that area, and
yeah, true.
But in any case, Botao, I appreciate that. It was an awesome presentation, and and keep us abreast on how this goes. All right.
Sure. Yeah.
Awesome. So, are there any other questions in the chat? We're running a little short on time, so I want to make sure I give our next speaker the time he needs. Jeff DuBose is currently a graduate student at the University of Notre Dame Radiation Laboratory under the advisor of Dr. Prashant Kamat. His research focuses on the photochemical and photophysical aspect of a class of renewable energy materials called perovskites. He studies energy and charge transfer events occurring in bulk and nanoscale materials using a variety of spectroscopic and electromechanical techniques. He is the recipient of the Graduate Fellowship of Notre Dame Energy and the Center of Environmental Science and Technology. And so he has research in biology, plants that undergo photosynthesis to convert sunlight into chemical fuels, and a longstanding goal of scientists has been to mimic that photosynthesis. And so he's going to talk about those chemical systems and what research he's doing to that end. Take it away.
Awesome. Thank you very much. Let me just get my laser pointer going.
Awesome.
Yeah, thank you so much for the invitation to give a talk here and for the introduction. Since I come from maybe more of a chemistry background, this might be a little bit of a departure from some of the talks that we've been given today. But with that, I'll just sort of launch into things. So when we're talking about energy transfer, I think it's kind of useful to talk about, where do we see energy transfer and why does it matter? So sort of as hinted at before, in biology, in these different photosystems that do, photosynthesis, we actually have multiple energy transfer events within those biological systems, in addition to electron transfer events. But these are very, very nascent and very important steps in that overall biological system. Now, a lot of chemists in our lab and other labs have actually looked at sort of, translating that into the artificial photosynthesis world using things that, man-made things like cadmium selenide quantum dots or different metal oxide particles. But those energy transfer events also still play a role there. Additionally speaking, if we think about our colleagues in biology and that use biological imaging, oftentimes there are these dye molecules that are fluorescent that actually, depending on the distance between those dye molecules, they can interact, and you can have different fluorescent lifetimes, different fluorescent colors, if you will. And that's important for different types of biological imaging. So, this energy transfer comes up quite a bit. And when we talk about energy transfer, generally speaking, we have light incident on some sort of sample that'll get excited into the excited state. That'll be the energy donor, and we have something that accepts the energy. And generally speaking, when we have these energy transfer events, it can either occur through a singlet energy transfer or a triplet energy transfer. And maybe it goes without saying for an audience like this, but when we talk about singlet states, we talk about a ground state and electron, and excited state electron having oppositely paired electron spins, versus a triplet state has the same electron spin in these cases. Of course, these singlet states have lowered lifetime typically, but they can also be directly optically accessed. Of course, in the triplet state, you have typically a longer lifetime due to that spin forbidden nature. And typically, you can't directly optically excite into a triplet state in most cases. You have to sort of access it a different way. But again, if we think about, sort of the applications of a singlet versus a triplet state, when we think about singlets, of course, a very important application is in photosynthesis. Of course, these are typically singlet energy transfer events that occur within plants. Of course, when it comes to triplet states, maybe it goes without saying again for this type of audience, people have been trying to use these molecular triplet states as different qubits. Of course, this isn't necessarily something that I am as familiar with, but I know that generally this is something that people are starting to look at in particularly molecular systems. Additionally, when you have triplets, you can also do some very fancy things. In the case of up converting or down converting light, you can actually have two triplet states in a molecule fused together to form a higher energy singlet state. And so people have been investigating this for actually extending the solar spectrum that's available to, for example, solar cells. But these are just some of the sort of examples of singlets versus triplets. Now, in the system that I'm looking at in this case, we're working with these energy donors, which are these cesium, lead, bromide, perovskite quantum dots. So these are little chunks of matter that are about 10 nanometers in size, sort of, somewhere between ensemble and somewhere between molecules. The nice thing about these guys is they have very high absorption coefficients, so they absorb light very well. And additionally, you have this nice surface that you can potentially, sort of self-assemble molecules onto the surface of the nanocrystal to sort of tether those and then have these different transfer events. Additionally, with these perovskite type quantum dots that I'm working with, they also have very tunable absorption and emission energies through what's called halide alloying, which is something I'll introduce toward the end of the talk. But that's the energy donor. In this case, the energy acceptor that we have is this rhodamine dye molecule, which is a very well-studied dye molecule, kind of a model system. It supports both facile singlet and triplet state formation. And importantly, the spectroscopic signatures for the singlet state and the triplet state in this particular molecule are very well characterized. So it serves as a very nice sort of model system. So the first set of experiments that we did to sort of look at the potential energy transfer events that are happening is we basically just have a cuvette full of our nanocrystals dispersed together. So this is in solution at room temperature. And what we do is we go on and we add the rhodamine dye molecule into that solution, and we let everything kind of self-assemble. And then we look at what happens in the photoluminescence spectrum. So this is the response in this case of the nanocrystals. They emit light at around 500 nanometers when excited. And so what we see is as we add more and more rhodamine, we get a quenching of that photoluminescence. So that tells us that there's some sort of interaction that's actually stealing the excited state, so to speak, from the nanocrystals. And then down here around 575 nanometers or so, we see a little bit of a hump appearing. And when I blow that up over here, this is basically the direct emission from the rhodamine dye molecule itself. So now we can look at what's happening at the energy donor in terms of its fluorescence and also the energy acceptor. So at this point, we don't really know if it's for sure energy transfer. It could be an electron transfer event. But what we do know is that there's some sort of, deactivation by rhodamine of the cesium lead bromide perovskite nanocrystal excited state. We can also back out some useful information from these photoluminescence graphs, but I'll sort of jump past that just for the sake of time. Now, to sort of further nail down whether or not it's energy transfer, we kind of do the reverse experiment. So now in this case, we just have a cuvette that's full of, in this case, the rhodamine dye at a constant concentration. And what we do is we go on and we add small aliquots of the nanocrystals to see what is the change in the emission of the rhodamine? How does it respond to the presence of those nanocrystals? So you can see this is sort of the weak and small emission from the rhodamine by itself. And as I add more of these nanocrystals, I see a stronger emission from that rhodamine. So that's what's graphed here. You can see the emission intensity versus the concentration of the nanocrystals. We get more of that emission coming from our energy acceptor in this case. So this indicates to us, okay, that we actually have most likely a single energy transfer event. Another thing too is, if it was actually the triplet state being formed, which has a more redshifted emission, then we'd expect the emission to be increasing out here around 650 nanometers. But since we see more of this emission appearing, and since it appears for where we know the singlet state emits, then we can expect it's primarily singlet energy transfer. Actually, I think this was mentioned before in a previous talk, but one way to really nail down is it energy transfer is to do what's called a photoluminescence excitation spectrum. So in this case, we have the same cuvette. We mix our nanocrystal and our dye molecule together in the cuvette, and we excite the sample over a range of different wavelengths. And what we do is we collect only the emission. We monochromate that down to 650 nanometers. So we're basically monitoring, okay, what is the emission response of the rhodamine as we excite at different wavelengths? So if we move, from right to left, from low energy to high energy, we can see that something starts to absorb around here that gives rise to the rhodamine emission. So there's one species that's absorbing, and then there's a second species here that's absorbing that's also giving rise to that rhodamine emission. And so the important thing is if I overlay the absorption spectra of the two, so we can see if we directly excite in the region where rhodamine absorbs, surprise, surprise, we get rhodamine emission. That's pretty straightforward. But importantly, we can see there's this very nice correlation between the absorption spectrum of the nanocrystals and actually this emission response from the rhodamine. So this gives us pretty clear evidence that yes, it is definitely singlet energy transfer that's occurring. And so the excitation of the nanocrystals gives rise to that response from the rhodamine. Okay, so now that we've established sort of what's happening in the system, the next thing we wanted to do was kind of probe what are the dynamics, or what is sort of the time scale at which this energy transfer occurs. And so we do what's called a transient absorption experiment. So this is a pump probe technique. And essentially, in step one of transient absorption, what we first do is just take a UV-Vis absorption spectrum of the ground state. So we can assume that most of the electrons are sitting in that valence band or that ground state, and we come in with a white light pulse and just take a simple absorption spectrum. The second thing we do in transient absorption is then we actually pump the system with a laser pulse. So in this case, this is a roughly 35 femtosecond, 400 nanometer laser pulse. That's going to excite a bunch of electrons into the excited state. And then while everything's still in the excited state on the picosecond to nanosecond time scale, since we don't have a lot of time to actually probe, we have to come in and hit it with a white light pulse. And that allows us to basically probe the excited state through absorption. And we can actually take a difference between the excited state and ground state absorption, and that's the actual spectra that we generate in this case. That's what I've shown here. This is the transient absorption spectrum first of just the nanocrystals. We see this nice response as a negative feature around 500 nanometers. This corresponds to excited electrons within the nanocrystal. And as those electrons relax back down to the ground state, we get a decrease in the signal. And so you can see when I have the nanocrystals and the rhodamine there together, I get two nice spectral features, one from the nanocrystals, one from the rhodamine. And if I blow that up there, you can see this is the weak change in absorption from those rhodamine molecules. So this is what we see in the spectra. The more interesting thing, though, is the actual kinetics, or how quickly do these signals go away in time. So if we look at, take a slice at 500 nanometers, if we essentially monitor the kinetics of the nanocrystals, trace A here, this is the nanocrystals just by themselves. This is sort of their inherent excited state decay. But when I add a bunch of this rhodamine, I see a faster excited state decay on this picosecond time scale. So again, that's sort of mirroring that deactivation of the cesium-lead bromide, the nanocrystal excited state. Really, the more interesting thing, though, is if we take a look at what's happening with the kinetics at the rhodamine side of things, around 570 nanometers. So what I've compared here, this is trace A is the rhodamine by itself. So if we have just rhodamine, no nanocrystals, when we excite the sample, we get an appearance of that singlet state, and then it starts to slowly decay on the picosecond time scale. Now, interestingly, when we have the rhodamine and the nanocrystals together, instead of having this near instantaneous appearance of the excited state, we actually have this nice finite rise time. And so the singlet state basically is appearing over roughly 200 picoseconds. And then after that, it starts to decay away. So it may not actually look like much, but the fact that we go from a near instantaneous to sort of this finite rise time of that signal, this is basically us being able to watch that energy transfer event occurring, which is pretty exciting for us. And I know I'm running a little bit on time. I'm just hitting 10 minutes, so I'll just try to go through. You can see this is the two kinetics graph together, showing that the decay of one is concomitant with the rise of the other.
You're doing fine. Take your time.
Okay.
Go ahead and finish.
Okay, so I just have a couple more slides. So if we ask ourselves, why are we seeing primarily single energy transfer? If we think about other systems that have, for example, acceptors that are like pyrene or naphthalene, those typically have fairly high level singlet energy states. And so it's very hard for most nanocrystals to actually sensitize all the way energetically uphill to access that singlet state. So in those cases, you see primarily triplet energy transfer. In the case of this rhodamine molecule, it's actually thermodynamically favorable to both potentially sensitize the singlet state or the triplet state. So that's why we think we're seeing more of the singlet state energy transfer happening because it is directly accessible. Okay, so the final thing we wanted to do was actually ask ourselves, what is the mechanism of energy transfer? Does it occur in Forster or Dexter type energy transfer?
Yes.
And so, of course, as you guys probably know, I mean, this is sort of needs more introduction for other audiences, probably not for this audience, but Forster energy transfer is this dipole-dipole coupling mechanism. It happens over longer distances typically. Dexter energy transfer is more of an electron exchange. The important thing is the rate constant of energy transfer for these twos. These have a very different formalism. But one nice thing is they both depend on this J term. And this J term is what's termed the spectral overlap integral. And this essentially looks at what is the donor emission and the acceptor absorption and how much do those two overlap. And it gives you sort of an idea of like how much in resonance are these two states. So you can see here for the cesium-lead bromide nanocrystals, this is the emission here, overlapping very well with the rhodamine absorption. So we have fairly good overlap. But one thing that we did, which is kind of fun with these nanocrystals, is if we actually add in a small amount of a chloride source and start alloying, so basically making a chemical alloy of the actual nanocrystals, make it a cesium-lead bromide chloride nanocrystal, that starts to blue shift or shift to higher energies the emission of the nanocrystals. And so now we can basically tune J somewhat arbitrarily just by adding in a little bit of chlorine and changing the parent nanocrystals. And that allowed us to basically investigate, do things in terms of the rate constant of energy transfer. Does it follow more of a Forster type or more of a Dexter type energy transfer? Okay, so real quick, in the last couple of minutes, these black circles here, this is the actual measured KET, that energy transfer rate constant. As we chloride alloy, as we shift J, we see that decrease. And now what we did was we said, okay, assume it's a Forster type mechanism. What would be expected in this case if it is purely Forster? And those are these blue squares here. We can see for cesium-lead bromide, which is the system we've been working with, we get fairly good overlap. So we can assume, okay, it's probably more so Forster in this case. But as we add more and more chlorine into the system, we start to really blue shift the emission. We start to change J. And eventually at these lower levels of J, we see over an order of magnitude difference. And so that implies to us, okay, there's probably more Dexter type energy transfer happening out here. But importantly for our system that we've been looking at, we can say it's most likely Forster type. Okay, with that, I'll just sort of wrap things up. So we wanted to see, is it singlet, is it triplet? We're seeing primarily indications that it's singlet energy transfer. Transient absorption spectroscopy tells us the time scale of that energy transfer. And importantly, this sort of chloride alloying trick really allows us to give an idea of, is it more Forster or is it more Dexter? So with that, I'll just go ahead and wrap up and acknowledge, of course, all these members of the Prashant Kamat Lab. My contact info is here if you want to ask any more questions about this stuff. And the paper for this actually just came out online today, so very excited about that. But there's some info down here if anyone's interested. And thank you again for giving me the opportunity to talk.
Jeff, this is outstanding. It's outstanding work. And so can you please put the paper link into the chat? I want to read this I mean, this is very exciting stuff. That's why I said take as much time as you like. Let's check the chat to see if there's any questions. Now I have a bunch of questions, but I know we're past time. So Jeff, what I'd like to do is me and you set up some time and discuss this. It's just outstanding work. There's a couple. There's a chat link here. Mm-hmm. Okay. That was you and the paper link.
Yeah, that was just me with the paper link.
Awesome. So I'm pulling that up now. Any questions? Yeah. All right. So with that, I'd like to thank all of the participants and all of the university researchers that presented today. And also thank you, QED-C members, for listening. And we will make sure that Jeff and the team and all the rest of the presenters get invited back when we have our workforce talk with the folks that have all of the opportunities so they can talk directly to those companies that they're interested in. That's one of the things that we're committed to do from QED-C, is to help these young people find opportunities in the quantum, on the quantum teams in the marketplace. And so with that, I want to thank everyone for coming today, and that's all we have.
Thanks, Charles.
All right.
Thank you.
All right,
Thank
guys.
you.
All right, Carol. All right, Mason. All right. See you guys later.